I wanted to work through a problem that involves the magnetic field of a long straight wire and the superposition of magnetic fields of a number of long straight wires. In this problem, we've actually got 4 current carrying wires. Each of them is carrying a current 5 amps. Those currents are, and those wires are, arranged on the 4 corners of a square of size 0.2 meters. And we've got to figure out the magnetic field that's created by those 4 current wires at the center of the square, at the center of the current carrying wire arrangement. The situation is pictured here, over here on the left-hand side. So the 4 corners where the 4 wires are marked A, B, C, and D. And the directions of the currents are indicated in red. So the 2 wires on the left-hand side, that's A and B, have currents flowing into the screen. The 2 wires on the right-hand side have currents that are flowing out of the screen. We need to find the magnetic field at the center of this arrangement. And the center of this arrangement, just by a little bit of geometry here, right-angled triangles, if the square is 0.2 meters by 0.2 meters, the center is 0.14 meters away from each of the 4 wires. So each of the 4 wires is the same distance from the center of the square because it's a square. And that distance is 0.14 meters by Pythagoras' theorem. Anyway, what is the field, the total field of the 4 wires at this center? Well, the first thing I'm going to do is actually draw the field at the center of the square by drawing the individual fields at the center of the square at the 4 wires, and then how those fields were superimposed to make the total field at the center of the wires. And then only after I've made a drawing will I go on and calculate the field at the center of the square. I'm doing it that way because the drawing of the individual fields and the resulting field will really help me with the calculation of the total field at the center of the wire. So let's go through the wires one by one, figuring out what their fields look like at the center of the square. I'm going to be using for this the right-hand rule and the application of the right-hand rule to a current carrying straight wire. And when you apply the right-hand rule to the current carrying straight wire, you're using the right-hand rule to figure out the sense or the direction or the orientation of the field lines, knowing the direction of the current. So in the case of wires A and B, the current is into the page. So I'm going to point my thumb into the page. And my fingers of my right hand will curl in the direction of the field lines, circling around, looping around the wire. For wire A, the field will look something like this. I'm kind of below the wire, and I'm to the right of the wire. And if I position my thumb at the wire, my fingers curl in this direction, below and to the right of the wire. So I'm going to label that as BA. It's the magnetic field of wire A. For wire B, again, that current is flowing into the page. I'm going to orientate my thumb into the page. My fingers will curl in the direction of the field, and they curl around at this location above this wire and towards the right of this wire. They curl around in this direction here. And I'm going to label that B, B. So those are the two wires on the left. Now I can do the two wires on the right. Two wires on the right, the field is heading out of the page. And then my thumb's going to be pointing upwards off the page. Again, I'm going to point my thumb in the direction of the current and use my fingers to indicate the direction of the field. For wire C, then the field lines are looping around the wire, and down here below the wire and towards the left of the wire, they're heading in this direction. My fingers point in this direction. I'm going to label that BC. And then finally for wire D, again, it's pointing out of the page. The current's flowing out of the page. I'm going to point my thumb in the direction of the current. My fingers will curl in the direction of the field. My fingers are curling above and to the left of the wire in this direction here. And I'm going to label that BD. Now, because this is a square arrangement, these angles here by geometry and these angles here by geometry are all 45 degrees. Each of the 44 fields is 45 degrees below the horizontal. Each of the four fields is pointing along either this diagonal, the one that I drew in, or pointing along this diagonal, the one that I didn't draw in. They're all 45 degrees below the horizontal. Two of them point towards the left and are 45 degrees below the horizontal. Two of them point towards the right and are 45 degrees below the horizontal. Because of the symmetry of this arrangement, because the currents are on a square, so the fields have this simple arrangement of being 45 degrees below the horizontal, two to the left and two to the right. Because the currents are all the same currents, 5 amps, the components of these fields that are acting towards in the horizontal direction, those cancel out. And the components of the field that acts downwards add together. So the net field is going to look something like this, pointing straight downwards. So now we know the direction of the resulting magnetic field. I'll call it BR. Let's see if we can figure out the size of the resulting magnetic field. To start that going, I'm going to note that the magnitude of the magnetic field of wire A at the center is actually the same as the magnitude of the magnetic field of wire B at the center, which is the same as the magnitude of the magnetic field of wire C at the center, which is the same as the magnitude of magnetic field of wire D at the center, because all the wires are equal distance from the center, all the currents in the wires are equal sized. So the two things that will determine the size, the magnitude, the strength of the field, the current and the distance are all the same. So all these four fields are the same. I'll just denote them then B. And the value of B, we can always calculate by this equation for the magnetic field of a long straight wire at a distance r from the straight wire. So it's equal to the current divided by the distance from the wire, multiplied by this constant of nature, mu naught over 2 pi. So that's the strength of all of the four individual fields. Now, what about the resulting field? Well, we've already made some arguments about the resulting field. The x component of the resulting field, so that's the horizontal component, I'll call it BXR. That's actually 0. It's 0 because there's equal components towards the left from two of the wires, A and D, as there are components towards the right from two of the other wires, C and B. So the horizontal components to the left and the right cancel out. There's no magnetic field left or right. BXR equals 0. The magnetic field downwards, and I know it's downwards from my picture, So I'm just going to put the minus sign in by hand. That magnetic field downwards, that's the strength of the field due to one wire times sine of 45 degrees to find its vertical component times 4, because there's 4 wires creating 4 downward components of the fields. So this is the equation for the y component of the field. And I can stick in the expression for the magnitude of the field due to any one of the 4 wires. It was mu naught I over 2 pi r times sine theta here, times sine 45 degrees. Okay, this point, we've got an equation for the strength of the downwards field, the y component, in terms of quantities that we know. So let's just fill them in. We've got a mu naught over 2 pi. Well, mu naught, if you remember, is 4 pi times 10 to the minus 7 Teslas meters over amps. So mu naught over 2 pi is just going to be 2 times 10 to the minus 7 Teslas meters over amps. So that's the constant. And then we got to multiply that by the current, which is 5 amps in each wire, divided by the distance from the wire, which is 0.14 meters. And then we got to multiply that by sine of 45 degrees. And if you put all those numbers into your calculator, you get a resulting magnetic field that is 20 micro Teslas in strength. So that's the y component of the field. As I say, the x component of the field up here, that was 0. The total magnetic field strength is therefore 20 micro Teslas strong. And from our picture, from our sketch, it's downwards. And so this was an example of figuring out the magnetic field that's produced by an arrangement of current carrying wires. It involved using the equation for the magnetic field of a single current carrying wire, coupled with the superposition principle for the 4 magnetic fields created by the 4 individual wires. It involved being able to sketch the magnetic fields of the individual wires and how they add up to make the resulting magnetic field of the arrangement of wires. That was important. And then it involved doing the calculation where we employed the equation for the magnetic field of a current carrying wire. It's proportional to the current, inverse proportion to the radius. We also employed some geometry in solving this problem. Geometry of a square, geometry of a triangle, Pythagoras' theorem, trigonometry, were all used in solving this problem to find the total magnetic field and the direction of that field.